The last unit in advanced functions on rates, we're doing very much the same thing. We know a little bit more about limits now. We've talked about it a little bit more, thought about just limits on their own, okay? And remember, I said this yesterday, like, when you look at just a limit and not its function, like we're gonna take advantage of limits now to do some interesting things. And we've already seen that, as I said, in the last course. But when you just look at a limit of just a parabola or something that's boring, it still does have its own definition as it approaches from the left and as it approaches from the right, right? It has its own definition. That's what a limit means. But then how can we use limits to solve more interesting questions? So that's what we're starting to get into today. And it says here, some limits can be evaluated simply by substituting, but then some cannot. Always remember this. Some questions you can just substitute. I sort of touched on that in that last example we were doing, where if you're asked about some other boring value that you could just substitute, then do that. Don't overcomplicate things. And in fact, we're going to get into the more interesting questions very quickly, but we're going to try to remember always sub first, because maybe the value just works and you just did a whole bunch of work for no reason. Right? So sub-mentally, you don't have to show that step. Sub-mentally first, make sure the limit value that we're approaching, so -5 in this case, make sure that it doesn't work. And we'll see what that means by doesn't work in a moment. But if it does work, just substitute. If it doesn't work, then you got to figure out which strategy you're going to use. And that's what we're going to spend a couple of days on figuring this out. So in this case, I just substitute. This is just straight line. I put -5 in, plus 7, and I get 2. There's nothing more interesting to it than that. And again, we know about that function from grade 9. It's such an easy one, but it's just a linear function. There's no breaks in it. There's no anything weird happening, so I can just sub in. If it was some other kind of function that I knew might, like, suspiciously have issues, then we would have to do some different work. But in this case, I know. This next one is a polynomial function. Now, there's a bit of a difference in notation here. It says f at x is this function, and then find the limit as x approaches -2 of f at x. So this is just notationally, this question is worded in a slightly different way, but it means the same thing. And this is a cubic graph. It's a polynomial graph. What do we know about polynomial graphs? What do you know about the domain of a polynomial graph? Picture what you know from the polynomials unit way at the beginning, units 3 and 4 of advanced functions. You know about polynomials. Picture them. They all have the same domain, and their domain is x as an element of the real numbers. X can be anything. Right? Isn't that true of every polynomial function? Whether it's linear or parabola or a cubic or a quartic or a quintic and so on, they're all going to be the same. And they may twist and turn and do all kinds of things, but eventually they just go off in either direction or something like this or something like this, and they'll go forever. So the domain is always x as an element of the real number. So again, every polynomial function, we know they're just boring in terms of limits. So I can just sub in. So this equals the limit as x approaches -2 of f at x, which is x cubed plus 7x minus 1. And oh my goodness, make sure this isn't where you make the mistake. So this is equal to -2 all cubed plus 7 times -2 minus 1, which is -8 minus 14 minus 1, which is -23. Don't make this like the brackets. Right? In this case, it worked out to -8 anyway, but oh my goodness, if that was squared, make sure you don't get the negative sign wrong, and that's where you make your mistake, right? Be careful with that. Those are the kinds of things like yesterday, you don't want those to be your mistakes. Domain and range is an important thing. That's something that you'd start learning about in grade 9, but it doesn't have a lot of context. And now, all of a sudden, in functions and in calculus, we start to really see its value. What's the point of domain and range? Because we're exploring these functions in much more specific and careful way. And so that's something that you should be very familiar with, domain and range. Like that's something that should be easy for you at this point, to write the domain and range properly and to understand domain and range and what it's talking about. Couple more examples. What about this one? What do I know about this one? Emily. Yeah, that's exactly right. It's going to be does not exist. 1 over 2 minus 2, which equals 1 over 0. Therefore, does not exist or equals does not exist. We talked about that a little bit yesterday. It doesn't exist because it's an asymptote. And even if it's approaching the asymptote and increasing on both sides, we still would say it does not exist. So if you're talking about a value at an asymptote, the limit does not exist. Right? We just know that. And again, anywhere else, if I picked 3 or 4 or 5, then it does exist and I could find it by just subbing in. But it happened to be asking about that one point where the asymptote existed, so it does not exist. What about this next one? Ooh, this one fools some people. So I'm going to sub in -4. I look at this value and I say, oh, this one will have an asymptote as well, but it's at +3. And this is asking about the limit at -4, so that's fine. So -4 plus 4 over -4 minus 3, which is 0 over -7. So what's my limit? What kinds of mistakes do you think people would say here? What do you think? Yeah. They might think it's undefined or something, I don't know. Or they might say it does not exist or something like that. Oh, that's just the y value. That just means that the 0 is the answer, just like if 1 were the answer, right? There's nothing wrong with this. 0 can be the answer. 0 in a numerator is fine. It just happens to be an intercept. Okay, everybody good with that? So those ones are pretty straightforward, I hope. So here we go. Let's substitute here. You might already see what's happening. You might say, oh, 0 in the denominator. Mr. Blair warned us about this. Does not exist. No, we can't jump to that conclusion. Okay, we have to do a full mental check. And so watch what happens when I sub -2. Again, I got to have brackets around that. When I square it, that's going to be super important in this case. -2 plus 2. What do I get on the bottom? I get 0. What do I get on top? -2 all squared, Aleph? 0 as well. And we did sort of see this, although we looked at it in a bit of a different way in MHF, but we did sort of see this. So this is a very different case from just a 0 on the bottom like we saw in example C. This one's does not exist. This one might exist or it might not. We're actually not sure yet. This is what we call indeterminate. And if you noticed that word in the title of this lesson, indeterminate limits. Yesterday we just talked about limits. Today we're focusing on indeterminate limits. So what do we do in this case where we get 0 over 0? That's what we're looking at today. Okay. So the limit might exist. We need to do some work to check. Over the next 2 days, we're going to learn all kinds of different techniques. And the ones we're going to do today are the ones we already did in MHF, so there's nothing really new happening, although there'll be a little bit more. It won't be necessarily as clear which strategy you're using. That's going to be a little bit trickier maybe. Eventually you're going to have to really learn how to decide which strategy to use, okay, when you get an indeterminate limit. But tomorrow is where we start to learn some new techniques. And again, mentally sub in, because if the bottom is 0 and not the top, then the limit doesn't exist because you're at an asymptote. But if both the top and bottom are 0, then it's indeterminate. You don't have to do this step. You don't have to show this step. This step would happen mentally, the substitution to check. We just did it once for our note to sort of explain what's going on here. So, let's go back to the original question. The limit as x approaches -2 of this function, x squared minus 4 over x plus 2. What do you think we should do to explore this further? Does anybody have a guess? Factor, and that is our first strategy. Again, picture what's going on here. What if I graphed that function, that original function, x squared minus 4 over x plus 2, if I graphed that, what would it look like? It would have a hole in it. When I factor it, I see the hole. That's what a hole is when you have a common factor in the top and the bottom, like factor of x. Not a common factor of 2, that wouldn't help. A common factor of x, x plus 2 over x plus 2. That's a hole in the graph. But what does a hole look like? Thinking about limits, thinking about the figure that we looked at yesterday, or the one in the learning goal today. It's a graph that's approaching this hole and meets it. It's not an asymptote where it's going up and going down or something like that. It is approaching the same value from both sides, right? So the limit there will exist in this case. So we do it the same way as in MHF, and we write out this step one last time that has the new function, and now we can sub in to figure out, we're basically peeking at the graph here. So that original function, x squared minus 4 over x plus 2, the value of the function isn't -4 at that point. But it looks like it's supposed to be. It just happens to have a hole there. Otherwise, that is where the graph would be. Any questions? It's MHF. So if you passed MHF and you're in this room, hopefully you understood at least that much where, yes, that's pretty straightforward. And usually people do well in the rates unit, so I'm not surprised if everybody kind of feels like, yeah, this is easy. I got this. This is no problem. But it's a bit of a different take on it, maybe, now that we've talked more about limits and not just finding slopes of tangents. It was kind of just a thing we did to find the slope of a tangent before. Now we're digging a little bit deeper into understanding what's going on. All right, let's keep going. Next one. So this is where, again, it starts to be like, you're going to have a whole bunch of different techniques that you can use to solve these. Which one are you going to choose? Which one is the right one? And I hope it's obvious so far. What do you think we should do? What do you notice about this question? Mason. Very nice. It's got a difference of cubes on top. What about in the bottom? Is the difference of squares good? So we can factor. So probably that's what we should do. And if you're good at factoring, which by this point I hope you are, you've already kind of at least partially factored it in your head and you know what's happening. So the limit as x approaches 3 of x minus 3 x squared plus 3x plus 9. And that's really important, what's left over. Because that's what's going to allow us to evaluate afterwards. And I get those two gone. And I'm left with this x squared plus 3x plus 9 over x plus 3. We should have done the mental check. I mean, we kind of did, but I should have mentioned it. What happens when you sub 3 in? That's a value that we're talking about finding the limit for. So 3 cubed is 27, minus 27 is 0. 3 squared is 9, minus 9 is 0. So it was 0 over 0, so indeterminate, right? If I subbed in the 3 into the original top function, you get 0 over 0. Always do that mental check. What about now? Am I going to get 0 over 0 again? I suppose that might be possible, and then you'd have to do more work. But I think in this case we're fine. So let's sub 3 in. Whoop. I'm subbing in now, so I don't need that. So it's 3 squared plus 3 times 3 plus 9 over 3 plus 3. So I've got 9 plus 9 plus 9, 27 over 6. And divide both the top and bottom by 3, I get 9 over 2. Everybody good? Okay. Limit as x approaches 0 of 1 over x plus 2 all squared minus 1/4. That's a little small. You can't see it very well. So mentally sub in. The denominator is obviously 0. What if I sub 0 into the numerator? So 0 plus 2. I'm looking at this part right here. 0 plus 2 is 2. Squared is 4. 1 over 4 minus 1 over 4. That's all 0. So again, 0 over 0. Indeterminate. So we need to do something. And it doesn't look like I can factor. It's not a polynomial over a polynomial that's factorable. So this is like fraction in a fraction. When you have all kinds of fractions, you might think of it this way. Fraction in fractions. What do you think we're going to do? I've seen this before. Yes, sort of, at least. Yeah, that's one of the things that we could do. How exactly would that look? There's sort of two different ways of thinking about this. Get a common denominator on top or multiply the whole thing by a common denominator of the top, right? So 4x plus 2 all squared over 4x plus 2 all squared. It works out the same. Like you might have seen it done slightly differently, or sometimes the solutions might look a little bit different, but it basically works out the same in both cases. So on the bottom, I get x times 4x plus 2 all squared. And what happens on the top? I get this times that, right? So it cancels the denominator. And I just get 4. And then for the other one, I've got negative 1/4 times this. So the 4s are going to cancel. And I'm going to get minus x plus 2 all squared. I hope that you could follow. That's just fraction math. Again, that's not the kind of thing that we want to be bothering us at this stage. If I subbed in at this stage, I'd still get 0 over 0. Like, we're not done yet. We have to expand and simplify to factor here. So limit as x approaches 0 of 4 minus x squared plus 4x plus 4. I want the bottom factored. It's factored. I'm not expanding that. So what's happening on top? I've got negative x squared minus 4x, and then the 4 minus 4 are gone. Hey, don't just copy me. You can take it from here. I'm sure you know what you're doing. I chose to factor out the negative. You don't have to. It really won't make a difference. But here we go. This is what we were working towards. And now I've got my x's There's the hole in the graph. So remove the hole, peek at what's happening behind it. And now I can sub in. So that's -4 on top and 16 it looks like on the bottom. 2 squared is 4 times 4 is 16. So -1/4. Again, I think that should feel familiar from MHF. Are we okay? So what have we seen? We've seen the factoring types. We've seen like when we have fractions, like rational functions, that kind of messiness. What's the next type? This one looks a little bit different from the type we were used to seeing in MHF, but it's the same idea. You could probably guess at what you do. What do you think? Kayla? Very nice. Okay, so we're going to rationalize. Which means multiply by the conjugate. What's the conjugate in this case? It's the square root of 9 minus x plus the square root of 9 plus x. And it's the same things. People do mess this one up and do all kinds of different things, but the whole point of it is that that sign there is supposed to be different from those two signs, but those two have to be the same, right? Plus over plus. So you're multiplying by 1. By 1. Something over itself is 1. So we're not changing the function. We're just going to change what it looks like algebraically. So on top, I get x times this whole thing. It's got to be in brackets. What do I get on the bottom? We're not going to do the whole long expansion. We need to know how it's going to work out. We need to know what a conjugate does, why we're using it, so that we can jump to the next step. Because otherwise, oh my gosh, it's going to be like the entire page long, right? It's too much to write out, and that's not the point. The point is we're supposed to know what the conjugate does. So what's my next line going to look like on the bottom? Go for it. 9 minus x minus 9 plus x. Very nice. It's like that difference of squares type thing, right? You've got the same thing plus and the same thing minus. So you've got both of them squared with a minus inside. That's what's happening there. So it got rid of the square root signs, and you're just left with what's under the square root sign. We call that the radicand. So we're just left with the radicand of each bracket. But we saw this in MHF. Sometimes, usually you only had one radical and then a constant or something. So that constant itself would be squared, and then the radical would just lose the radical sign. So 9 minus x minus 9 plus x is 9 minus 9, which is gone, and negative x minus x, which is negative 2x. We got it. Let's see, the square root of 9 minus x plus the square root of 9 plus x all over negative 2. So that's 3 plus 3, which is 6, divided by negative 2. The whole thing gives you negative 3, I think. Questions, questions, questions. Those are the 3 types that we're looking at today. Again, they're all from, so with fractions, common denominator of fractions, factoring, and rationalizing. But I've got a bunch more examples. We might have time to get through one more, I don't know. But it's just more of the same types of questions. And I'm going to let you try to get started on it, and we'll just see how far we get. So what do you think we do here? Has everybody started the first step? I decided to multiply by the conjugate. I chose to start with the denominator. So again, 5 plus the square root of 27 minus x. Don't change the sign in the radicand, or in the radical part. Don't change that sign. It's just between, right? And on top, look at how I wrote this out. So I've got this whole big mess times this whole big mess, all in brackets. That's really important. But I'm not actually going to expand that yet. And then what happens on the bottom? This is sort of what I was talking about before. So you get 5 times 5, which is 25. And then you get the thing positive and the thing negative, which add to 0, like the difference of squares guy. And then we get square root of 27 minus x times itself. One's positive and one's negative. So I end up with minus 27 minus x. But it's not going to factor until I rationalize the whole thing. Well, sort of, at least. So I've got to do some work on top. So I've got to do it again. And this is new. I don't think you saw questions like this in MHF. So I'm going to multiply by the conjugate of the top, of the numerator of the original. So plus 7 plus 3 over the square root of x plus 7 plus 3. So I did it twice. And now, if you want to just watch for a minute, that I'm going to multiply this by this, right? Those are the ones that I'm choosing to multiply by. You could, it's this times this times this, but I want to multiply the two that are conjugates of each other. So I get x plus 7 times x plus 7, so that's just x plus 7. And then I've got negative 3 times positive 3, so minus 9 times 5 plus the square root, 27 minus x, still all in brackets. And now I've got 25 minus 27 plus x. And what do I notice happens here? So I've got x plus 7 minus 9. Remember, all of this started because it was indeterminate. It was 0 over 0 when I subbed in 2. So this factor of x minus 2, the part that's making it indeterminate, has to be what eventually factors out. It's got to work out that way. So I should expect that to happen. So it worked. What we did worked. X minus 2 over x minus 2. I can get rid of that and sub in and solve the rest. Any questions? We don't have time for another example. I think I have one or two more, but yep. I do. I just forgot to write it. Thank you for pointing that out. It should be there. So this whole thing should be like this, and this should be there. Plus 3, and it should still be here as well. Absolutely, you have to. Yeah. Thank you. This one, I'm gonna do this one and post it just in case you want to look at it. It's only different because it's got a binomial that is cubed, so it's still a difference of cubes on top, but it's one of those messier ones. So if you just want to see what that expansion looks like or how you do the factoring there, okay, I'll put it up online. And this one is just another factoring question, but there's one little thing to it that I wanted to point out. So again, I'll put it online. Maybe we'll get a chance to talk about it tomorrow. And then here's your practice. And again, those will be posted, but those are just some questions that are not really in the homework, but they're just different ways of thinking about things, different things to think about. So it gives you something to sort of think about that's different. Say that again? Yeah.